Welcome all. So we'll be starting with our next session, and the topic of the session is predicting black swan events, and McKerns would be presenting on that. Michael has over 15 years of teaching experience in physics, applied math, and computing, and has taught 20 financial science workshops in past years alone. He has been a research scientist at Caltech since 2002, where he has served as a project manager and also a lead developer for two 15 million software projects on predictive science and large-scale computing projects. Yeah, welcome.
Thank you. Thank you. I appreciate you all having me out here. So I came a long way, and I'm enjoying PyCon India for the first time. So today, what I wanted to talk about was predicting black swan events. So I have the main developer on some software called Mystic, that is a framework for highly constrained nonlinear, non-convex optimization, uncertainty calculations, and risk. And it utilizes some of my other software, Pathos. It's a framework for heterogeneous parallel computing, management, and graph execution. I have funding from all sort of agencies. Up here you can see NSF, some Department of Defense, Energy, etc. So this work is in conjunction with these guys, mathematicians who invented Humanawati, who invented the new mathematical uncertainty framework. These guys were his students, and these are my developers. So what are black swan events? Black swans are high-impact, rare events. And black swans strongly impact risk, uncertainty, the probability of failure. So what they do is they're events that are supposedly very hard to predict. They're considered actually impossible to rigorously predict. But if you do predict them, it typically will yield you an enormous payoff. And it doesn't necessarily have to be in finance. Black swan events are in really almost everything. So black swans are, again, they're game changers. When you have data and you look at observed data and you try to predict the future, a black swan is an event that changes, let's say, how the stock market goes, changes combat scenarios, war games, strategic planning. Black swans can be seen in drilling and oil exploration. So if you think about it, what it is if you were to just drill randomly on the planet, you would never find oil. But there's a vein that you might find that you can't detect because it's deep under the earth or deep under the water. And you try to predict where that vein is going to be to minimize your loss. And when you strike it, a good vein, you get oil. So that's the same type of thing as you see in the stock market for hedge and portfolio risk. When are you going to have the big payoff? When is the crash going to happen? And actually the same underlying mathematics in drug design, mortality, and insurance risk. So they're everywhere, and they're actually, the place really to look for them is wherever corporations spend a lot of money trying to predict the future. So why is a black swan so hard to predict? Well, it's because hardly anyone attempts to solve real-world problems. Real-world problems are high-dimensional, nonlinear, non-convex. Every new piece of information adds a new constraint, often a nonlinear constraint, so they're a big, nasty optimization problem. Every piece of data, every model, every assumption, that's constraining information. So you're creating a big, nasty, nonlinear, non-convex optimization problem. So what do people do? Typically what they do is they start to reduce the problems by using strong approximations or building smaller models, models that approximate the behavior. When you start to do that, what happens? The calculations are expensive anyway, and the mathematics and the software to solve it rigorously did not exist until just recently. So this is just what everyone has done. So look at these, the two things. Most common thing people do is you have an unknown probability distribution. You have an unknown distribution. You don't know what you're sampling out of. So what people do is they assume what the probability distribution looks like, usually from data. If you've done Bayesian analysis, it's priors. Okay? And when you assume what the probability distribution looks like, then you can only predict the black swans that you've seen already. That means you can only see what you've observed already. As soon as you fix a probability distribution, you'll not see any new ones. And the second most common thing that people do is they assume a normal distribution and start to extrapolate. So when you see something like that, and when you see standard deviations being used, standard deviations being used away from Monte Carlo simulations, then what you're doing is you're seeing an averaging of behavior, which completely wipes out the ability to predict black swans. So the two most common things that people do are basically get rid of their ability to predict these things in the first place. So here are some kind of simple things that people do. You look at an optimization like this with try to get to the bottom of the well with no constraints. It's actually an easy thing to do. And as soon as you start to add constraints, well, it's a little bit harder thing to do. But what if you had a surrogate model that looked like this? And you said, I only want it to be valid within that window. And that starts to be a hard optimization problem to do. And what if you had these data points and you said, well, I want it to be valid where my graph has to go through those data points, then most optimization frameworks can't handle it. So we're already in something this simple and this low dimensional at a place where optimization frameworks start to fail and people have to use approximations. They use approximations like penalty functions. They approximate with convexity, use surrogates and wipe out the data, throw away the data, use this best fit surrogate, or again, worst case is extract a probability distribution and throw away the data again. So again, what if you have these black dots here and you say, okay, I'm going to assume a probability distribution looks like this, and then everything else will only be sampled out of that probability distribution. But then your next data point might be up here, and your probability distribution that's best fit, again, now looks very different than the one you just had. Right? So that would be what a black swan event would look like, totally changing your probability distribution right there. But really, what you have to do is you have to do this differently. You can't make these approximations and be able to predict rare events. So the subtle point is that approximations were done to make the problem solvable. However, they remove your ability to make these high-impact rare events predictions. So again, what people are doing is they're removing their ability to explore unknown probability distributions and reducing the problem to one of classic probability theory. So classic probability theory is from 1812, Laplace updated in 1933, and basically the idea is probability distributions are approximated as things that are known, and then standard deviations are used to reintroduce the unknown. But that absolutely, like I said, kills your ability to do and predict black swans. How does this differ from rigorous calculations of risk and uncertainty? In rigorous calculations of risk and uncertainty, we say that probability distributions are unknown, and we have to solve for them in the course of an optimization. And the first unified uncertainty theory was published by Awadi, myself, and a few of the other authors earlier this year. And it basically gives us the ability to address these questions directly as large-scale optimization problems. So what everybody does in uncertainty is, if they have a problem that says, I have 100 colored balls in a bag, and I'm picking out red balls, if you actually have data that says, on average, 10 balls are red, what's the likelihood of picking a red ball the next time? You can address that question directly, right? You don't know how many balls are in the bag, but you know on average they're 10. So what people usually do, what people have done up to this point, is they say, okay, 10 balls are red. Now I can calculate very easily the probability. But that removes rare events, right? The rare event might be when there's no red balls. Or so with this new theory, we actually can calculate the likelihood of picking a red ball explicitly based on the information we know. What's the best case and the worst case? And these three questions right here will give you the hedge. That is the definition of what people use to get the hedge. What are the bounds? What's the average? And the distance between those are the hedge. The distance between the bounds are the value at risk. So this framework can be used on things like the stock market. Okay, so I won't go through too much of the math. That's not for this conference, right? But the idea is, I just want to show you expectation value of some quantity. What we're actually doing is we're saying the expectation value is, on average, 10 balls that get picked out of the bag are going to be red. So we need to write things in terms of the expected quantity of interest. And the thing we're optimizing over is the probability of the system, which we don't know, and also the governing function of the system, which we don't know. But that's okay. That's okay. What we do is we collect all of the information about the problem into constraints, this A. That says anything we know about the system, we can write it as a constraint. And by imposing the constraints on the problem the right way, on the optimization problem, we encode all the information that we know about reality without any approximations. And we can get the limiting behavior, maximum, minimum, and most likely, for that problem. If you know how to write the optimization problem, and you know how to impose the constraints without approximation. Okay? So that's what that mathematics says. And here's actually how it's written. The lowest bound, based on that information, is equal to the expectation value over your unknowns. And it's less than the upper bound. So you know that the expectation value for your system has to be in between your lower and your upper bound based on those constraints. And you actually can write the formula for your upper and lower bound based on those constraints, like inf, which means a minimum, or sup, which means the maximum of this probability distribution. Which means, what are we doing? We're optimizing over probability distributions, something that's not been done before. And again, I won't hit too much math on here, but the point is that statistical estimators, priors, optimal bounds, they're just optimization problems. And they're big, nasty, ugly, mathematical optimization problems. This one says, right here, the optimal prior, which is the most likely probability distribution that gets you the best sampling to collect your Monte Carlo samples or whatever out of, is the minimum of the maximum of the expectation value of the expectation value of a function that represents your data minus your model of your probability distribution, right? That's ugly. And also, you should think it's probably pretty expensive, too. And the reason that people don't do this is because optimization, one, the mathematics didn't exist for it a few years ago. And number two is that this is multiply nested optimization problems over a probability distribution where we're definitely talking about nonlinear and non-convex. And most optimizers, the best optimizers in the world, don't go past 10 to 15 constraints in the nonlinear sense, right? So it just can't be done. Well, it just couldn't be done. So one of the things we've done as a project with, we've partnered with, like I said, the Military Department of Defense and some hedge funds, Google, IBM, this one is shock in microstructure materials. And basically for a material, this is nuclear weapons testing. Okay, so what happens to materials when you have a shock wave, and how does the material react? So what they do is they have two cylinders smashing into each other, where there's some microstructured material in each of the cylinders, and you try to predict what happens with the shock fronts. So the real system is basically a description of the cylinders, the microstructure, C of X, the chemical composition, and what you're going to look at is all of these things. And in the theoretical system, you have the equations of state, the mesh, everything that's a physical constant is a lambda. A lot of parameters to deal with. Very high-dimensional problem. And again, the point here is, if you have a simulation like this, it's going to be a big, nasty optimization problem, but we know how to write it now, right? How do we write the model error? The model error is the actual model error measured minus the theoretical model error with the parameters of the cylinders and the physical parameters of the material. I can write the statistical error. I can write the model uncertainty. I can write the probability of failure. This is the probability that the model, the difference between the model and the actual value is greater than A, is less than some epsilon, which means, is it likely or not that I fail? So all of this stuff, here again, the optimal bound on the statistical estimator, it looks just like the other optimization problem we wrote. But the point is, we can write this, right? For the first time, we can write optimization problems that can solve these type of problems. And what that means is rigorous statistics, statistical estimation, becomes an extremely high-dimensional, non-convex, nonlinear global optimization problem where we have to solve it exactly to guarantee our predictions. Right? As soon as we start throwing approximations in there, assume the probability distribution, we're lost. No black swans. Can we do it? Hell yes, we can do it. So with this new mathematical theory and MYSTIC optimization package and the parallel and distributed computing package of Pathos, we now have the ability to start solving these problems. So we need large-scale parallel and distributed computing for a lot of the big problems. You can run small computing problems on your laptop. I've run them on that laptop right there. But as soon as you get into real problems like these cylinders smashing into each other, then you need big, large-scale computing. You need asynchronous computing, monitoring, caching, archiving, job restarts, all the large-scale computing stuff, batch execution of the model. But if you look at optimizers, you look at optimization technology, what do you see? Optimizers are notoriously serial. They're asynchronous, diagnostic, limited, fixed execution strategy. They're actually the opposite of what's required to do these large-scale calculations. So what I had to do was I had to go in and rewrite the optimizers from scratch and customize it to run on these large-scale graph execution frameworks with the idea of abstractions on the programming model. So if we want to be able to have them run on multiprocessing, threading, MPI, SSH, GPU, or the cloud with a bunch of different schedulers, what we want to do is we want to write things like this. If anyone's familiar with multiprocessing in Python, what you do is you do a one-line configuration of a worker pool, and then you pick the map you want to use, and it's a map reduce, right? So from Pyena launchers, import slurm pool, which is a queuing system. Give me 16 nodes, 8 processors per node. Now I have my worker pool, and then I say I want a blocking map. Now I have an MPI-based blocking map that works on a cluster system, and then I can evaluate, just like a Python map, my model for the 16 numbers in MPI parallel on a machine. So that's what my Pathos package basically brings. Python is a sub-package of it. And if you want to do the same thing with parallel Python distributed over clusters, you can do that. Same thing. Here's IPC pool over some servers and get a asynchronous map this time. And again, it's a map function. This time, as you can see, it's asynchronous because you say get afterward. This basically gives you 80 to 90% performance of doing the thing by hand, but it just took me 2 lines. And now I'm launching jobs on clusters. And so what you get is you get the ability to build a parallel graph like this, make an extraction on the graph, and run between a number of different resources. So that's what we want to do. We want to run these big problems in parallel, any which way we like, fast parallel or large-scale parallel. We want it to work on a laptop. We want it to work on clusters. We want to be able to use sub-resources and nest the parallel computing. And all it is these map functions. If we use a map function and we have the ability to serialize all of Python, and I can do that with my package dill, then what we can do is nest all sort of parallel graphs and build the structure we need to do to solve these big problems. Now we need to be able to hook that into an optimization problem. So instead of a one-liner, I do have these written as one-liners, but what I can do is I give a very flexible, highly configurable interface where the key thing is my optimizer has state. Okay, and I can take my optimizer, and I showed the one-line interface for it, but this also I can say, where is this guy? Differential evolution solver, and here's my solver. I can set the save frequency, so it'll actually pickle and save the entire solver every 100 cycles. I set my initialization points. I set up monitors. Now these monitors, they work parallel distributed. So if you hook up a monitor, it's setting up the stream, and it feeds back the results of the best fit for each generation or every single evaluation. And those guys can be configured too. I can also configure the termination conditions. So that's one of the best ways to actually flexibly solve anything is to set the termination conditions. And it's a unique ability in my optimization package to be able to do that. And then we solve. We solve for a particular model and a particular termination condition, and we get our best solution. Now what I do is I have a bunch of diagnostics that you can go into, but then what you can do is, because it has state, right? It has state, like I can solve it here, save it here to a pickle file. It also has state because it's a class. So my solvers are all classes. And they have internal state. And that means I can take one that's already run. I can change something, like the termination condition. Here what I'm doing is I'm coupling together 2 termination conditions and changing the tolerance. I can restart the solver. Okay. So I have diagnostics coming off a solver. I can run in parallel distributed. The diagnostics can stream out. I save the state. I can restart. Really very flexible. Even if you're just doing some very basic optimization, this becomes a very powerful tool. And to extend the optimizers to parallel, all I need to do is build my map function and then say right here, set evaluation map, right? Set evaluation map with my map function, save that to the state of the solver, and now I start solving where the evaluations are done in parallel. So I can do that with a evolutionary algorithm and send all the evaluations off in parallel, or I can do it at a bigger range where I can actually run, if I have a cluster of 10,000 nodes, I can run 10,000 optimizations in parallel, each running an entire optimization problem itself, with the goal of all trying to find not the best solution. I can set it so it's the best solution because I can customize the termination conditions. I can pick however I want it to try to solve. I can actually try to map out the entire potential surface with 10,000 optimizers and have them report to me each local minimum. That's something very important in physical chemistry, to be able to solve the entire potential energy surface. So you can do that very simply by saying set the solver map, set the nested solver, and here we're basically using, again, parallel computing, and we're nesting two solvers inside of each other, right? So this is doing large-scale parallel computing on a very, like a PAL directional solver is a gradient solver. So it's fast global optimization. Okay, so we see problems like this. Again, this cylinder impact with lots of physics in there, and running these things on a large-scale cluster can take some time. They're running in parallel on Glory, which is one of the largest computers in the world, and it's taking a whole bunch of cores to be able to calculate it. It's already MPI scaled. And now this is my optimization framework. Whoops, it's my optimization framework. Running it over a period of 8 days. 1, 2, 3 machines, 3 of the biggest machines in the world. And also the one in Caltech's basement, which is smaller. So 4 machines over 8 days at, was it 20, it's actually 2117 petaflop calculation. That's an optimization problem doing sensitivity calculation of what are the most important parameters in 2 cylinders smashing into each other. And it's all run from my laptop. So we have the ability to do that. And actually the great thing about the code is I can run this petaflop calculation with the same code that I can run on my laptop. And I do absolutely nothing but change the lines that say run on the big resources, right? I don't have to rewrite any code. I don't have to write any MPI code. I don't have to write any distributed code. All I do is make the replacement back here of how the thing is going to run. So hooked up to an optimizer gives us this great ability to do predictive science at a large scale. Okay, so parallelism, though, is not enough. Like I said, most optimizers cannot handle larger than 10 nonlinear constraints. The way I write constraints is completely, well, for optimization, it's completely new. But if any of you have done physics, quantum mechanics, set theory, what you'll see is there's the concept of an operator. And an operator says if you have a set X and you apply an observable to it, you now get a new set. Okay? And what that does, it takes information and it constrains a set. And it constrains a set by applying the operator and reducing the set. If you have a set of 100 things and the constraint operator constrains it to be only the 10 things, then what you get is the set of 10 things at the end. Right? So I use that principle of applying constraints, applying information through operators to reduce the set. And what that does is that allows me to explicitly, without approximation, as long as I can write the operator, I can apply any information to the optimization problem. And the beautiful thing about it is, unlike a penalty, which is an addition, it's a multiplication or a filtering. So it's embarrassingly parallel, which means now all the information I apply can get farmed out in parallel and solved independently. And if it's coupled together, so what? It's actually just a big nonlinear optimization problem to solve a constraint. And that just means another nesting of a parallel optimization problem, and so on and so on and so on. It's big and ugly, but we already know how to do it. We have the infrastructure to do it. We can solve these problems explicitly. So I give the ability in Mystic to do symbolic and statistical constraints, to build exact constraints due to data points and surrogate models, and it scales up without bound. I've not run into a problem that's too big for it to solve. And I give all sort of neat things like memory caching, etc., for large-scale computing. That's part of either Pathos or Mystic, and they work together. So how do I write penalty functions? Penalty functions can be applied in general to any optimizer. And this is the thing that I said you typically don't do, but you can do it if you like. It's a decorator. With penalty, pick the type of penalty, and then just apply it to a penalty function. And the penalty function says, I'm going to make sure x has a mean of 5. And that's the way that people apply penalty functions, but I can apply it to any of my solvers. Here is doing the same thing, applying the mean of 5 to a constraint. And now this guy, what he does is, instead of applying a penalty function, what a penalty function does is it says, I apply this penalty to the things that don't satisfy the constraint, which means you're still exploring all of space, right? So if you apply a filter like this guy, and it says, only let the optimizer pick places where the mean is equal to 5. And what that does is it says, this space here or this space here, don't even let the optimizer go there. And then when you have some big nasty problem like that, and you apply data point and all these other constraints, actually the optimizer will only search in the white space, which is where the real solutions are. So that's how it looks. And you can build constraints like that with a variance of 10, blah, 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 and say set strict ranges, set constraints, and there's my constraints function. And you can do this with Monte Carlo methods or statistical probability functions, any of the uncertainty quantification stuff we've seen. Uncertainty quantification, now, what we can do, how do we write this on probability functions? So what we do is, here we have constraints, right? Here's our probability function, our wave function. Here's our constraints operator, and here's the valid wave function, right? So what we're doing is constraining, with all the information we know about the problem, the probability distribution. But what we're doing is we're writing the probability distribution as a basis set. And this is done a lot in quantum chemistry, right? That's how you solve for atomic problems, basically. But it's not done in optimization. This says what is the weight and what is the position. And that, therefore, it takes a probability distribution that looks like this and represents it by positions and weights of these masses. And that allows us to take these discrete items and have the optimizer move them around and get a representation exactly of what the probability distribution looks like. And if we have enough of those masses, we can basically build any probability distribution. It's just expensive. And here is a three-dimensional case of basically, this is a ballistic test. Again, military ballistic test. And it's a probability cloud at the beginning. And over several optimizations, the probability kind of shakes out into a 2-point. One is failure case, and the other is a scenario that's non-failure. And what it looks like is boom, 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 boom. And over 7,000 iterations, we basically start to reduce down to a point where we actually know the critical scenarios for success and failure. And if I'd drawn the picture better, you could see the weights instead of just having 2 black dots. The weights being the colors of the dots. Okay? And how does that actually look in the code? You have something like this, constraints. I have a product measure. I'm converting the optimization parameters to a product measure. If the mass of the measure is not 1, then normalize the measure, right? That means you have to have the sum of all things, the sum of all masses equal to 1, the sum of all weights of the masses equal to 1. And now here, since I said I want to work on an expectation value, like on average, 10 balls are red out of this times we run it, right? On average, I want the expectation value. And if the expectation value is not within my target, plus or minus some error, then set the expectation value to be the target. And that's me applying a constraints operator. So if it's not what I want, then make it what I want. And that's how my constraints work. It forces the optimizer to only pick valid points. And then my cost function is I have a product measure, and I want the probability of failure for my model in terms of the product measure, which means give me the probability distribution that yields the information on the probability of failure for my model. I'm directly asking for what the probability distribution looks like, and this is the maximum, and if I didn't have the minus sign there, it would be the minimum. Those are my bounds. That gives me the value at risk for the problem. So I can write it directly in Python. It's actually pretty simple to see how it works, and I've done things like large-scale calculations of risk, synaptic networks, semiconductors, prediction of earthquakes, ballistic impact, and just basically this is another ballistic impact problem where we can actually use this formulation to now start testing, well, what if this were true? How would it improve the model? Right? And when you do that, you now have a framework for improving, not just guessing a model and testing it. We have a framework for testing new models, testing and improving your understanding of these big, nasty, complicated problems. This is something that is absolutely unique on the planet. Right? So there's no other framework that can do something like this. Not only in Python, but on the planet. So we have the only software on the planet of rigorously solving for uncertainty and risk in large-scale, realistic problems. With OUQ, that's Owadi's mathematical framework, we pose our questions as optimization, optimize over the probability distributions, all possible scenarios, and use Mystic's constraint solvers to reduce the search space to the valid problems. So we're preparing new releases of our software to be released later this month. You can get them here. It's all open source. I don't release models to the stock market, but I do release framework, okay? So you can write your own and then do calculations. It's on GitHub. I have track sites, and I am always looking for contributors, collaborators, business partners. I have my own business that I partner with companies to do this. Best place to contact me is McKerns at Caltech. So thank you very much.
So we have 5 minutes for questions here.
Nice talk. Basically, I personally aspire to be something like you. But some people say that stock market is a random walk. Others say it's not. Is there any test that you can apply to basically make sure that you are not chasing a statistical ghost?
Right. So it depends on the question you ask, right? And what you'll see is it doesn't matter the level of randomness. If you ask a bad question that can't be framed in such a way to get an answer, then you'll be chasing a goose, right? But if you ask a question that's framed in such a way that regardless of the randomness, regardless of the type of randomness, where you can write the question like I did in the first few slides, like it has to be a targeted thing. What is the likelihood, or what is the maximum value? What's the likelihood that this particular portfolio will exceed a certain gain, will lose a certain amount based on market conditions right now? So if you say something like that, and you give as much information about the market, you can predict those questions. Yeah.
So I saw you had a lot of functions for predicting events and getting probability distributions and errors. Now the package contains all these functions, is what I understand. Like, so are these specific to predictions in physical terms, as in collisions or markets?
No.
Or could I use it for training a robot model or something like that,
Yes.
where I would potentially need such things?
It's generic mathematical risk and uncertainty, and all the things I've used it for material science. I've used it for earthquake science. I've actually working on some partners with some partners right now at HP and Cray and Google for predicting the time of a parallel calculation, right? So it's completely abstract. There is, if you wanted to use it for something with robots, you can.
Hi.
Yeah.
So I don't really have much of a clue about optimization. I come from machine learning, and the problem we have there is, I mean, it looks like you just want to fit a highly dimensional model. And the biggest problem we have in machine learning with a huge feature space is overfitting. And you didn't seem to talk about it.
Yeah, so for machine learning, what's done is machine learning and typically uses something like Bayesian analysis or an optimization up front, right? And the optimization up front, just like with Bayesian, what people do is they try to predict what the governing behavior is right now. And you basically build a probability distribution and then build a model off that probability distribution. In machine learning, you often just build the model off of the information you have. With the Bayesians, what they do is they build a prior, and then that's built off of a probability distribution that they fit to the current data, and then you build a model off of that. All of those things, what they do, and that's what I said in the very beginning, all of those things, what they do is they assume a probability distribution, and therefore you won't be able to predict black swans. You won't be able to predict these rare events. So they work in cases where you're predicting the behavior of something that you've already seen, and it doesn't deviate too much from that. And you know in machine learning what starts to happen if you get a real nonlinear system, it applies for a little while, and then you have to go back and adjust parameters and start again, right? So this is different. What we actually do is say, I only want to constrain the system with the things that I know, and then let the probability distribution be found as part of the optimization problem. And it actually scales up to very, very large sizes. So that was luck on my part for that to happen.
I just have two questions. First one is just a fundamental question. I know you talk about predicting black swans. So if you read Nicola's book on the topic, what he says is that black swans are impossibly difficult. I think you mentioned that as well. So I think my question is more like the fundamental nature of a black swan is that there is not enough information right now in the past and right now to predict it, right? So you are talking about an information loss there, right? So if you're talking about actually predicting them, what is the
Sure. So the reason that people say, and in his book he says it's impossible to predict, is everybody does predictions based on the past, right? Everybody does predictions based on the past, and so what you get is everybody tries to build these probability distributions, right, like this, based on data that you have already. And what that does is when you start sampling off of these probability distributions, you're only sampling off the events you've seen already. So it's impossible to ever see an event that happens out here, and that would be a black swan that completely changes the behavior. What I do with constraints, what I do with an optimization over probability distributions, is to say never select the probability distribution. Let the optimizer find the probability distribution as it's going. And what do I do with information is I say, I now, again, don't make any assumptions. I just reduce the search space to the places where the constraints are valid. And what that says is you don't see the black swan, but you leave a place for it to happen. Like this space, if this satisfied all the constraints, I don't even need a data point there. But because all the constraints are valid, it's open searchable space by the optimizer. And the probability distribution can find it. And you can find things that are these rare events you never see.
Thanks a lot. Last question. What features of Python, made you choose a language so as to fit this, solving this particular, problem?
Yeah.
I saw Decorator and that was amazing to see, So could you just briefly say about it?
Sure. The real thing is I started writing this 10 years ago, and there wasn't anything that could do it. And I was running a lot of projects at the time, and Python was the only thing that I could do where I could manage a project and go back and code at the same time. And one of the things I wrote back then was this serialization piece of code that it's called DIL, and it serializes all of Python. And when I have that, then I can ship all of my code out. I can ship my functions out anywhere I want across another process on other machines. And it basically gives me ability to, if I have code that runs it, then I can run on several different machines very transparently. And as soon as that happens, I said, I want to stay out of C. I want to stay out of these higher performance languages, because with Python, I can put the code there and run it and collect it back again. And so I started to build everything. No C, no complicated anything, no compiling, just Python, because it's fast to go back and forth. And that's what really did it for me. Yeah.
It seems to me like you're depending on constraints. And your constraints are what are your prior programs. Because if your constraints are wrong, or if your constraints are going to be excluding certain events, then it's not going to solve.
Sure.
In some ways, your prior properties are the constraints.
Yeah, so that is a great observation. And actually, this slide right here at the top, I didn't talk about this part, but here's your prior, right? Bayesian, here's your prior. Those are how I write my constraints, right? So I actually, one of the things I do when I go to companies who use Bayesian and machine learning as their current method, and they make approximations and they pick a probability distribution, I say, don't pick the probability distribution. Let's do that as a prefactor, a pre-step, and get the optimal prior, the best probability distribution. And then you can sample off of it and do your machine learning and do whatever Bayesian you like, but you'll be sampling off of the best answer instead of one you picked. And that allows everybody in those companies to do stuff at the same speed, with the same code, but get working off of a better, actually the best solution. So yes, it's direct parallel, except I don't make the critical strong approximation that those techniques do that allow me to get these black swan events. Yeah, if you have wrong information, wrong answers. No problem.
Yeah, thanks, Mike, for a wonderful presentation.